Welcome to the Deep Dive, where we slice through complex research to bring you those crucial insights and often unexpected facts. Today, we're diving into the pretty astonishing world of large language models. You've definitely seen their incredible progress, and maybe you've wondered about the secrets behind their scaling behaviors. We're here to dig into some really fascinating new research. It might just reveal a surprising secret behind how LLMs get their power, especially when they get multiple attempts at a task. So the big question for us today is, how predictable is their performance, really? And what's actually underpinning these specific scaling laws we keep hearing about?
Us, right. And the core of our discussion really comes from this fascinating paper. It's got a bit of a playful title, How Do Large Language Monkeys Get Their Power Laws? It's a piece that cleverly builds on some earlier foundational work. You've got large language monkeys, scaling inference compute with repeated sampling, and also best of N jailbreaking, both pretty recent, 2024. So what we're exploring is how these models' success rates, how they change when they get multiple shots at a problem or maybe a particularly tricky prompt.
Okay, so our mission today is to unravel this kind of curious contradiction, understand this sort of mathematical why behind it all, and then figure out how these insights lead to better ways to, predict and optimize AI performance. I'm honestly really curious about this one, and I think you're probably in for some serious aha moments. Let's unpack this. So, researchers have consistently seen something pretty remarkable when large language models, things like Pythia or the big frontier models, GPT-4o, Claude, when they make multiple independent attempts, let's call it AK attempts, at some task, their average success rate improves in this incredibly predictable way. What's really striking, though, is that the negative log of this average success rate, it actually falls as a power law with the number of attempts, K. For those of us maybe not deep in the math weeds, how should we picture that? A power law curve like a KB. What does that shape really tell us?
Yeah, that's a great point. So a power law. Imagine a curve that drops pretty steeply at first. You get big gains with the initial few attempts. But then the improvement starts to slow down significantly. The curve keeps going down, meaning you are still improving, but the gains get smaller and smaller with each extra attempt. It never quite flattens out completely, unlike, say, an exponential decay, which would suggest you're hitting a hard limit much faster.
Okay, that makes sense.
Yeah.
Faster gains early, then diminishing returns, but never zero returns.
Exactly. And we've seen this pattern pop up across different kinds of tasks, which, really suggests it's a robust finding. For instance, in that large language monkey study you mentioned, they looked at math problems and coding, and they found precisely that. The negative log of the average success rate across all the problems was approximately a KB, where A and B are just constants for that specific model, and K is, yeah, the number of tries. And then you have the best of N jailbreaking paper. Hughes and colleagues looked at trying to get multimodal models to respond to harmful prompts, jailbreaking them, essentially. And guess what? They found the exact same power law relationship for their attack success rate, the ASR. The negative log of the average ASR also fell as a KB. Consistent. Oh, and just a quick clarification on terms. You might see sometimes people talk about coverage, like the fraction of problems solved. That's basically the same idea as average success rate. We tend to use average success rate because coverage sounds a bit binary, like a problem is that either solved or not. The reality is often more nuanced.
Right, success can be partial sometimes. Okay, so that predictability, that's powerful. It means we can actually forecast how much better a model will get if we just, give it more compute, more chances.
Yeah.
Sounds simple enough on the surface, maybe even a bit too simple, but this is exactly where it starts to get really interesting and kind of puzzling.
It really is, because intuitively, if you just think about one single problem, right? A specific math question, maybe. If a model has some fixed probability, let's say P, of solving it on one try, then the chance of it failing 30 times in a row should drop off exponentially, like 1p raised to the power of k. So mathematically, the negative log of the success rate for that single problem, dash log passing at k, should actually fall exponentially with k, not like a power law. That's just basic probability for independent events.
Okay, yeah, that makes sense for one specific problem, and the researchers actually checked this. Did they confirm that individual problem performance does scale exponentially?
They did. That's the crucial piece. They managed to isolate the behavior for individual problems or individual prompts in the jailbreaking case. And yes, whether it was Pythia models on math problems or the big guys like GPT-4o on specific jailbreaking prompts, the per problem success rate, or rather the negative log of it, scaled exponentially with more attempts, K.
Okay, so now we have the riddle clearly laid out. Individual problems get solved exponentially faster with more tries. Makes sense. But the average performance across a whole benchmark set of problems improves much more slowly, following a power law. It really does feel like individual sprinters getting exponentially faster, but the team's average time only nudges down slowly. How can both things be true? What was the breakthrough here?
The breakthrough, the real aha moment, was realizing the answer wasn't just about the model's learning or anything like that. It was about the problems themselves. Specifically, it's all down to the distribution of difficulty. How are the single attempt success rates that PASI at one value spread across all the problems in the benchmark? That distribution holds the key.
The distribution. Okay. How does that work mathematically?
So the paper actually proves this quite rigorously. It shows that you get that aggregate power law scaling for the average success rate with exponent b if and only if the distribution of those single attempt success probabilities, PASI at 1, itself behaves like a specific kind of power law near zero. Its density needs to grow like a power law as the success probability gets really, really tiny. The exponent of that distribution's power law near zero turns out to be B1, so there's a direct mathematical link.
Whoa, okay. So the overall scaling law is basically a direct echo of how many really hard problems there are.
Pretty much.
Yeah.
Imagine you have a benchmark. Some problems are easy, PASI at 1 is high, some are medium, but crucially, imagine there's a long, long tail of really, really hard problems. Problems where the chance of solving them on one try, PASI at 1, is incredibly tiny, practically zero.
Like 1 in a million chance or something.
Yeah, exactly. Now, even though giving more attempts helps you solve each of those super hard problems exponentially faster individually, the sheer number, the density of problems piling up down there at those near zero success rates means that as you increase AO, you're constantly encountering new, previously insurmountable problems that are just barely becoming solvable. This pile up at the hard end acts like a drag on the average improvement rate. It slows the overall progress down from exponential to this power law crawl.
That's a fascinating way to think about it. It's like you're climbing a mountain exponentially fast, but the mountain itself keeps getting infinitely higher just ahead of you, because there are always more peaks.
That's a pretty good analogy, yeah. There's always a fresh supply of harder challenges just coming into reach, slowing down your average ascent rate. And the empirical data totally backs this up. When they looked at the actual distributions of PASI at 1 from those studies Pythia on math, Clojman and GPT-4o on HarmBench, they found these distributions did have those characteristic heavy left tails that pile up near zero success probability. Often they could fit them really well with something called a 3-parameter Kumaraswamy distribution, which is just a type of distribution that's flexible enough to capture that specific shape, that heavy tail near zero.
And didn't you mention a case where this didn't happen, which actually confirms the theory? The Llama 3 model.
Yes, exactly. Yeah. That was a great piece of confirmatory evidence. The Llama 3 8B instruction-tuned model, when tested on the jailbreaking task, didn't show that aggregate power law scaling. And why not? Because, well, it turned out it could be successfully jailbroken on every single prompt they threw at it within their sampling budget.
Ah, so there was no hardtail. No pileup of prompts it found nearly impossible to jailbreak.
Precisely. It didn't have that crucial heavy left tail in its PASI at 1 distribution for that task. So, no tail, no aggregate power law. It fits the theory perfectly.
Okay, this is making a lot more sense now. The distribution is the driver. So what are the practical implications of knowing this? Does it change how we approach things?
It absolutely does. This deeper understanding isn't just, theoretically neat. It directly leads to a new and potentially much more efficient way to predict that power law scaling. The researchers developed something they call a distributional estimator.
A distributional estimator. How does that work differently from just, say, running lots of tests and fitting a curve?
Well, the big challenge with the standard approach like least squares regression on the average success rates is getting accurate data for those really hard problems. If a problem has a 1 in a million success chance on a single try, you need a huge number of samples, a huge K, just to see it succeed even once or twice and get a decent estimate of its PASI at 1. That's computationally very expensive.
Right. You might run out of budget before you even solve the hardest ones.
Exactly. So the distributional estimator takes a different tack. It assumes the overall distribution of PASI at 1 follows a known form, like a scaled beta distribution, or that Kumaraswamy we mentioned. Then, instead of needing precise PASI at 1 values for every problem, it focuses on fitting the parameters of that assumed distribution. Critically, it fits them so that the fraction of problems predicted by the distribution to have very low success rates matches the observed fraction of problems that you couldn't solve at all within your sampling budget, your empirical hard problem bucket.
Ah, so it uses the proportion of unsolved problems to infer the shape of that crucial hardtail,
without needing to measure each tiny probability directly.
Precisely. It leverages the known mathematical link between that tail shape and the overall power law exponent b.
And does it work better? Is it more efficient?
According to their tests, yes, significantly so. When they compared it against standard methods like least squares, the distributional estimator showed significantly better sample efficiency. What that means is it could estimate the true scaling exponent b much more accurately, especially when you have limited data, maybe fewer problems in your benchmark or fewer attempts per problem. They reported something like an order of magnitude lower relative error in estimating b under those conditions.
Wow, okay, an order of magnitude. That's a huge deal.
It really is.
So for anyone actually building or deploying these LMs, this isn't just academic theory. This is a practical tool. You could more accurately predict the compute needed to hit a certain performance target, make smarter trade-offs.
Exactly. Imagine you need your model to achieve, say, 90% average success on a tough benchmark. Before, estimating the compute needed might have involved a lot of extrapolation and guesswork, especially about those hard problems. Now, using this distributional understanding and the new estimator, you can potentially get a much more principled, data-efficient forecast of the number of attempts, and thus the inference compute required. That helps you budget better, make more informed decisions about model size versus inference cost versus performance. It provides a much clearer picture of those trade-offs.
That really does sound incredibly useful.
And it might even have broader implications. The paper sort of tentatively suggests this distributional viewpoint might also shed light on other scaling laws we see in AI, like the power laws related to pre-training compute and model size. Maybe similar distributional mechanisms are at play there too. It's all about understanding these fundamental scaling behaviors, which ultimately helps the whole field build better, more efficient, and more reliable AI.
Okay, so let's recap. We started with this surprising but consistent observation. LLM average performance scales like a power law when you give them more tries. Then we hit the contradiction. Individual problem performance scales exponentially. And the resolution, the elegant mathematical truth, lies in the distribution of how hard problems are on a single try. Specifically, that pile-up, that heavy tail of really difficult problems dictates the overall aggregate power law behavior.
That's it in a nutshell. It shows that this seemingly simple, predictable improvement we see at scale is actually this really fascinating interplay, right, between how hard individual problems are and the overall statistical character of the whole set of problems. And it definitely raises a further question, doesn't it? If that distribution of difficulty is so absolutely critical for how these things scale, how much control do we actually have over shaping those distributions? Could we, through careful benchmark design, or maybe even during model training itself, deliberately shape that difficulty distribution to get even more predictable or maybe even more efficient scaling? That's something to think about.
That is a fascinating thought. Can we curate the challenge to optimize the learning curve? Well, we hope this deep dive has given you a powerful new lens, a new way to look at the truly astonishing world of large language models and how they scale. Keep thinking, keep questioning, and definitely keep digging deeper.